What was that?
That's all.
Okay, very good. Yes. Very good. All right, so welcome everyone to yet another one of our colloquia. Today we'll have a team presenting to us. I'll tell you a little bit about them. Dr. Diana Davis completed her PhD at Brown University in 2013. She was a postdoc at Northwestern University for 3 years, followed by a visiting professorships at Williams College and Swarthmore College, and she now works at Phillips Exeter Academy in New Hampshire. Her research is in geometry, mostly in dynamical systems such as billiards. In summer 2020, she organized a group of 40 students, including Quinn and Katie, to do data science research, collecting and analyzing data to combat gerrymandering ahead of the 2021 redistricting. She has subsequently worked with a few students, notably Corinne, on independent research in the pure math questions around gerrymandering. Quinn Basewitz is a sophomore at Swarthmore College, intending to major in computer science and math with an emphasis in statistics. Outside of math, she is on the field hockey and track teams. Katie Knox is taking a gap semester from Swarthmore College and is joining us from Albania. Corinne Mulvey is taking a gap year between high school and matriculating at Harvard, during which she is doing research in graph theory and its applications to gerrymandering and redistricting, and also tutoring younger students in math. So yes, without further ado, please take it away.
Thank you. So this, our first slide, we have all of the students that were a part of the project this past summer. And then the 4 of us that are here are boxed in red. So we're going to be talking about assessing congressional districting, gerrymandering, and graph theory. And before we get into the mathy side of it, we first want to talk about what gerrymandering is and why this is relevant. So congressional seats are reapportioned every 10 years after the census, because in the House of Representatives, every state has a different number of representatives based on their population. And the census reports changes in these populations, and then the new districts reflect those changes. So you can see in the map on the right, this shows how many representatives each state has, and since the past census, how that has changed, whether they've gained or lost population and therefore representatives. And the thing about this is that the people who are in power at that time are the ones that redraw the maps. So the incumbent politicians, the ones that are in power, can increase chances of re-election by gerrymandering, which we'll look at on the next slide. So gerrymandering is the manipulation of boundaries within state or congressional maps for purposes of partisan gains. So we can see the first picture, we're looking at the map of precincts. We'll talk about it in a bit, but a precinct is basically where you vote. So we're looking at just that body there, and we can split up this, this shape, the whole state per se, that we can see is 40% Republicans and 60% Democrats into different ways, so that with 5 districts, a different number of them end up with Republican representation versus Democratic representation. So there's different types of doing this. There's packing and cracking, which dilutes the voting power of opponents. And there's, we can see in the second picture, then the Republicans are cracked. And there's 5 districts that are all won by by Democrats. And then the third picture, the Democrats are packed. So they're smushing most of the Democrats into 2 of the districts so that the Democrats win 2 and the Republicans are able to win 3, even though they have a minority overall. And because of this, constituents are sometimes misrepresented and the opposition is muted. And there aren't any federal guidelines in place to prevent gerrymandering. So each state can do this differently. So some are better than others based on what laws they have written for how the state should be districted. So talking about scales of political geometry, the smallest thing that we can look at are the census blocks. In most states, this is just like a city block. but it depends how many, like how dense the population is for how big of an area that represents. And this is the smallest level of geography that you can get basic demographic data for from the census, because they can't report data on an individual level data just because of privacy reasons, but we can get data down to this level. And then the next size is census block groups. These are made up of the census blocks. I forgot to mention, this is New Hampshire, where the lines are showing the different scales of that geometry. So census block groups are groups of census blocks. So it's the next biggest that we can look at. There's about 39 blocks per census group, and we can get more information about the people that live there from the American Community Survey, which reports data at a broader level, but it's still pretty small in the groups of people. And then one of the most important ones for us are precincts. So the precinct is where you vote. Everyone that votes at that same polling location is in your precinct. And these are also made of census blocks then. And you can't, when we're looking at redistricting, we can't split these precincts because everyone that goes to your precinct gets the same ballot. So they have to be voting the same across whichever election it is at that date. Then the next biggest is counties. These are smaller geographic areas than states, but still have their own legislative power. In some states, counties are relevant for redistricting, and they have laws that they should not split counties as much as possible when drawing the districting maps. Other ones, counties are pretty much irrelevant and they can ignore them. So it depends where you're looking. And then the last one is congressional districts. So everyone in your congressional district has one representative in the House. And this is the main thing that we're looking at drawing in different ways, whether gerrymandering is occurring here so that there's misrepresentation in Congress. So then we've shown that there's different ways they're fair, unfair in representing people, but we have to have some sort of way to measure whether it's fair or not. So the first one is partisan symmetry, which is one way we can examine gerrymandering. So this is the principle that a particular vote share received by a party should translate into a specific number of seats, regardless of which party received that share of the vote. So in the graph below, it shows that when Democrats receive 60% of the votes, then it translates to 82% of the seats. Or when Republicans win 60% of the votes, then it also translates to 82% of the seats. And it has 180-degree rotational symmetry so that it doesn't matter which party wins that percent, they'll get that percent of the seat share. And it goes through the 0.5. So if one party gets half of the votes, they should get half of the seat share. And then in the 2016 election, when Donald Trump won the election despite losing the popular vote, partisan symmetry standard was not met because the Democrats had over 50% of the votes, then it should have been the majority to win. But because it didn't go through that point there, then it was not met. Another way we can evaluate fairness is through the efficiency gap. And this counts the number of votes that a party wastes in an election to measure whether one party had a systematic advantage in gaining seats through their votes. To calculate this, any votes cast for a losing candidate are considered wasted, as are any votes for a winning candidate in excess of the number needed to win. So if we have one district where the Democrats win 40 and the Republicans win 60, then all of those 40 are considered wasted. And the 10 above 50%, because it's already past the majority, are also considered wasted. And this is quantified by convention as total Democrat wasted votes minus total Republican wasted votes divided by the total number of votes. And it represents which party had an easier time converting their votes into seats. In this graph on the right, the efficiency gap for many simulated districting plans for the 2014 state Senate election in New Hampshire is plotted. The slightly negative average efficiency gap means that Republicans have a more difficult time converting their votes into seats in New Hampshire. And of course, as ideal with partisan symmetry, we want the efficiency gap to be 0, so that neither party has a tendency to have more of their votes go to waste. Now I'll pass it on to Katie to talk about our experience with Maine.
Hello, everyone. I'm Katie, and I worked on the data collection and analysis of the state of Maine this summer, but I'll be talking mostly about the data wrangling process. So like the end goal and the data wrangling process was to create a shapefile, which is just a file type that defines digital polygons based on their geographic location and allows you to attach data to each of those polygons. So in this case, the polygons we wanted were precincts. And if you recall the scales of political geometry that Quinn was discussing, we needed to combine 3 kinds of data: election data, demographic data, and shape data into one shapefile. And if you remember, the demographic data is reported by census blocks. So in a way, we needed that data to go up a level into precinct shapes to attach individual census blocks to precincts. And then we needed to merge election data, which is reported at the precinct level, with the definition of the polygon also at the precinct level, in order to be able to analyze how congressional districts, which are made up of these precinct shapes, may be created using bias based on partisanship or race. Next slide. Oh, sorry. Could you? Okay, thanks. So yeah, the collection process was fairly straightforward for the state of Maine, because the state government website provided a shapefile with just the polygons of the precincts. And in Maine, it was quite straightforward because the election data was reported by a town. And so towns and precincts are almost 1-to-1 in Maine. So I'll talk a little bit more later about the small discrepancies we ran into, but for the most part, this was taken care of by the fact that towns and precincts are essentially the same. And as you can see on this picture to the right, the state of Maine is quite uninhabited, and that caused a few issues that I'll talk about later on. Next slide. So one issue that that other teams ran into this summer was that not all states are as organized as Maine and don't always provide a shape file. And that was the case with Nebraska. Their state, they contacted the Secretary of State, I think, if I remember correctly, and they just sent them a PDF picture, essentially, of where all the precincts were. So that team needed to go in and manually look for street intersections that matched up with where they looked like they were on the picture, essentially, and do the same thing with census blocks. In order to actually be able to give a geographic location to these shapes. So clearly that process took a little bit longer. Next slide. Yeah, and so in Maine, the main issue that we had was small discrepancies where in those uninhabited areas that I showed before, oftentimes there was only a handful of votes reported in a township. So the township would get reported they would group together townships to report them. And this varied sometimes from election to election, how specific townships were grouped together. So essentially we just had to create a standard. So essentially normalize the data in order to have one consistent reporting record. And then on the other hand, we had to reflect these decisions in the actual shapes themselves so that we could have one unique identifier of precinct for each record. And yeah, that was the most tedious part for sure. Next slide. And we also ran into other shenanigans, such as this small lake that is, small island that was floating in a lake in the middle of Maine. So when we finally were trying to use a software to combine election, demographic, and shape data, we kept getting this very mysterious error. And we spent like a week or so combing through the different data sources and trying to make sure that each town was like literally named exactly the same across each data source, but the issue turned out to be just this small island that had no adjacencies. So we just declared it as adjacent to the nearest precinct, and then all our problems went away. But yeah, it was a tedious process. Yeah, I'll pass it on to Corinne.
Can you, so there's a question in the chat. Can you go back to the shapefile slide about with the state of Maine, the first one?
Yeah. Yeah, for instance, I think if you go to that slide a little bit more on the shapefile, I think if you look at the picture, this is like this is an image of that is produced using the shapefile data. If that makes sense, it's just a way of like describing what the shapes are and where they are. And then you can see this highlighted precinct towards the bottom of Maine. For this precinct on the right, we have all the data that is attached to that precinct in the shapefile. So at the top, you can see that there's Pres 16R, and that just means the presidential election data from 2016, the recorded votes for the Republicans, and below that, the Democrats. And towards the bottom, you can see like top pop is the total population. And then there's additionally different racial ethnic categories that was obtained from census data. So this was kind of like, this is the end result of our whole process, is being able to attach election and demographic data to a specific precinct.
All right, so I will show mine now. It's over to me. So here we go. So you might wonder how, oh wait, this is not, oh, made a mistake. There it is. There's the top. Thank you. Sorry about that. Okay, so as Quinn said, we have these metrics of whether things are fair or unfair, and we want them to have value 0. So for instance, there's the picture on the right, and Quinn mentioned that you want this graph to go through 0. So you want to aim for value 0. But it's quite difficult. And I think that aiming for value 0 is sort of like asking for a pony for your birthday. Like, first of all, it's unreasonable. And secondly, if you were going to get a pony for your birthday, you'd have to make so many ridiculous changes in your life, so many sacrifices in order to have that it wouldn't really be worth it. And so if we were to try to concoct districts that had 0 for these measures, sometimes it would be really difficult, and we probably wouldn't be going for what we actually want to go for. So the new way of doing it, and also, yeah, you can't really, people had a really hard time justifying why like mean, median, or efficiency gap was the holy grail of best ways to measure. So the new paradigm is sampling, checking whether things are outliers. Oops. Is the new way. So let me tell you what's going on. Sampling. So you might think like, okay, you've got a districting plan. Let's see how it is against all other possible districting plans. Like, okay, the Democrats won this many, the Republicans won this many. Let's just see how that is across all the others. But this problem is actually way too big. So for instance, even in this little toy state here, Iowa is like has 99 counties that you can break up. This one is only 7 by 7, so it's 49 counties that you can make into districts. But there are 158 million ways to cut this 7 by 7 grid into 7 districts. And for a 9 by 9, there's that really large number, maybe 706 trillion. And for a 10 by 10, roughly the size of Iowa, it's just impossible. It ran on the supercomputer for over a month. So it's just infeasible to try to compute all possible districting plans and then measure the one you have against them. Especially, for like a reasonable size state like Pennsylvania. I mean, it would take longer than until the heat death of the universe. So there's no time to wait for that. We have stuff to do. So here's how we sample. So here's a proposed districting plan of our toy example of a 7 by 7 state that we want to break into 7 districts. We use a process called recombination to randomly explore the space of redistricting plans and sort of visit a representative sample. So we can see billions or trillions of plans, which sure is a lot, but it's less than the total number of plans. And that's fine because we'll see a representative sample, we hope. So here's how it works. You take 2 districts and you merge them, and then you resplit them. You take 2 more districts, you merge them, you resplit them. So here's how, so let me just do it slowly. First, you take 2 regions and you combine them. And what you actually do is you create an adjacency graph. So what I mean is you take all the precincts that are touching each other along an edge and you draw an edge between them. And then we find a spanning tree. So this is a graph theory concept. A spanning tree is a subgraph of the original adjacency graph that touches every node and also has no circuits, no loops. So there's a spanning tree. And then we find a place where we can cut the spanning tree so that you have equal population. So we want 2 equal population districts just like we had before. In this toy example, equal population is going to be equal number of blocks. So 7 and 7, which is what we have here. And then we resplit it. And then we just do that. We merge them, we find a spanning tree, we cut, we have 2 districts. We merge them, we find a spanning tree, we cut, we have 2 new districts. And we just keep doing that, jing, jing, jing. And we just wander around the space of plans for as long as we want. Yay, life is good. So let's do an example. So here's Orange Pinkland. These slides are made by Moon Duchin, who's a mathematician who works in this field, who trained us. So here's a 10 by 10 grid. We could call it Iowa. With 40% orange voters. So those are the orange ones and 60% pink voters. And you might wonder, if you're going to make 10 districts, how many should orange win? You might think they should win 4 out of 10 because they have 40%, or maybe 3 out of 10, or who knows what you think. But you can think about how many they should win, to be fair. So here's one way of blocking them up. This is a sort of a Midwestern aesthetic. So there's no blocks in which orange has a majority, but there are 3 in which orange has a tie. So there's sort of like a toss up. So we might say orange on average wins 1.5 in here in plan A. And here's plan B. This is sort of a North Carolina type aesthetic. Here there are 6 orange seats. So there are six districts where orange has a majority. I think, good job, orange. So here's what we do. We start with the plan A and we want to see, like, is it an outlier? Is this reasonable? So what we do is we start with this plan and then we run the redistricting, the recombination algorithm. So as you can see, what do we have? In the first plan, orange won 1.5 seats, and in the second plan, orange won 6 seats. So what happens if we just randomly wander around? Well, this is what happens here. Let's do it again, starting from the original plan and wandering around. Let's do it again. Okay, so it's looking pretty reliable, like same thing every time. And 1.5 is seeming like a pretty reasonable number of seats for orange to win. We would also have accepted 2, 2.5, 3, 3.5 as reasonable because they're all in sort of the fat part of the visible part of the distribution. Let's start with plan B. So we start with this plan that's shown and we wander, we recombine and resplit, recombine, resplit 100,000 times. Okay, that's the first run, second run, third run. So wow, you might think that if we had started with this plan where orange wins 6, that they would sort of keep winning a lot. but no, this actually, even though we started in a different place, this histogram looks a lot like the first one. So this makes us believe that this is a reliable system, because it doesn't really matter where you start, you explore the whole space. And in this case, we would say 6 is an outlier. Probably the person who drew this map had some motive other than just following the laws when they drew this map. So this is our new paradigm. This is how it's going. We are using this outlier analysis to tell when we think things are gerrymandered. So let's do an example for a real state, Pennsylvania. So in the fall of 2018, I was teaching at Swarthmore College, and Katie Knox, who just spoke, was in a discrete math class with me, and we were talking about maps and gerrymandering and redistricting, and it was very exciting because Pennsylvania had just determined that their voting map was unconstitutional based on the state constitution in Pennsylvania. They'd thrown it out, and they needed to make new maps before the next elections. So they brought in Munduchin, mathematician, to help them evaluate it. So there's Pennsylvania. There are its 9,000 precincts, and that's the 18 districts in the enacted plan. Swarthmore is somewhere down here near Philadelphia. It's kind of hard to see in this picture. Population density is high. So they ran this 2 to the 30th times, which is like what, 1 billion, and compared the enacted plan to 1 billion other plans. So the enacted plan is what's at the top. So that's the current plan, current at the time that this picture was drawn. And as you see, when you start there and you do the recombination, you get this histogram that's way far away. So it tells you that probably whoever was drawing this map had some kind of ulterior motive. The picture on the left uses the mean median measure of fairness, and the one on the right uses the efficiency gap. So these are 2 different measures that people are using, but you can see that it's an outlier, and in particular, it's a Republican favoring outlier. So in this metric, the higher the number, the more easy it is for Republicans to convert votes into seats. So they determined it was unconstitutional, so they needed to do a plan. The Republican legislature proposed a new plan. They posted it on Twitter. That's how they proposed it. So if you start with that plan and you run, you get the same kind of thing. So it's still a high outlier in the Republican favoring direction in using both of these metrics. And then the governor, Tom Wolf, whose picture I showed on the previous slide, he was a Democratic governor, proposed his own remedial plan. And you can see that it is in the visible part of the distribution. And even in this one, it seems to be, well, yeah, it seems to be on the Republican favoring side. So this is a measure, this is a way to measure whether things are outliers. Now, the original way that people tried to measure gerrymandering was by seeing if the metric was like above 0 or below 0. And so now I've marked where 0 is on all these pictures. 0 is just unreasonable, like asking for a pony. That's not where the distribution is at all. If you wanted to get your map over to 0, in all, well, maybe in this case you could get to 0, and maybe in this case, but usually you'd have to basically do a bunch of gerrymandering just to get your map to 0, which is not our main concern. That's not what we care the most about. So this is how it's done. We looked at New Hampshire, as Quinn showed some pictures of it. I'm currently in New Hampshire. We looked at it last summer. Let me tell you a bit about New Hampshire. So in New Hampshire, there's mountains, there's 16 miles of seacoast, there's Exeter, where I am, there's this big lake, Winnipesaukee, and then the 2 population centers are Concord and Manchester and Nashua, 3 population centers. Okay, so what do their congressional districts look like here in New Hampshire? Okay, this is what they look like. So when we saw this, I said to myself, that is a gerrymander, because it looks like it goes zigzag back and forth, zig, zag, zig, zag, zig, zag, zig. And so we thought, well, we're gonna certainly uncover something here. But one thing, actually, while this is overlaid, one thing you can notice is that there are 3 population centers, Concord, Manchester, and Nashua. And it does sort of like grab one and leave the other 2. It kind of makes sense that you'd want to split them. Fair enough. Okay. So we looked into them. And actually, we didn't find much evidence of political gerrymandering. So here's the same picture Quinn showed earlier with the enacted plan shown on it. So it's right in the middle of the distribution. So no evidence of gerrymandering here in this metric. Here's another way. This is just not using a histogram, but we we looked at what 100,000 plans or something like that, and looked at the district with the smallest percentage of Democratic votes and the highest percentage of Democratic votes, and then made a box plot of, you know, where the most of them tended to fall, and the average, and the enacted plan, which is the red dot, is right in the middle. So I've seen this picture for Utah. The red dot is like way outside for Utah. For New Hampshire, it's right in the middle. So no evidence. This one does not support evidence of political gerrymandering. Unfortunately, with only 2 districts in New Hampshire, and often both like a majority for one candidate, like a 53% majority, most of our histograms tend to look like this. So one place where you could help is to come up with a metric that we could put on our x-axis of our histogram that would work for a state with only 2 districts. And it's not just New Hampshire. There's actually lots of small states with only 2 or 3 or even 4 districts. That's most of the country, not California. But you could help another state. You're nice people. So you could come up with some metric that works for these small states. That would be super. Got to have something to put on the x-axis. And I just want to give a little introduction to Corinne, what Corinne's going to talk about. I mentioned the recombination algorithm. So we combine regions, we create an adjacency graph, we find a spanning tree, we cut for equal population, but sometimes our trees just don't work. So what do you do then? Well, you ask Corinne what you should do then. And another time it might not work is if you combine regions and then you want to resplit to make new regions. But look at this. No matter how you resplit the new regions, those 7 blocks are going to have to be together. So there's only really one way to recombine. So my point here is that this problem of gerrymandering, which is a very applied problem that comes from real life, introduces these really interesting pure math problems that are simply pure math. And you can do pure math all day and just think about graphs and trees, and you can help the world. So let's do it. All right.
Okay, so, oops. So the question that I looked at had to do with what Diana said, which was tree splitting and splitting trees to make new districts. And so there was a few problems with just drawing any spanning tree over 2 merged districts. The first one is that it might not have an edge that you can cut to make 2 equal districts. And the other problem actually comes from when you apply this to real world data as opposed to just a grid. We are looking for to resplit the tree into 2 districts that have equal population, but not necessarily equal area, because districts aren't really concerned with area. They're more concerned about equal population. So here's an example of the 5x5 grid. But instead of having districts of equal number of blocks, I've split them into districts that have approximately equal population. So there's some deviation about 1 or 2 between each of the total populations of each of these districts. And so the question that I was looking at is, when can a vertex weighted tree be equally partitioned into 2 equal weight pieces, approximately equal? So to do this, we do the same thing that was mentioned before, which was we merge 2 districts into a single district and we draw a dual graph over them. But this case, the dual graph has weighted vertices. And then we draw a uniformly random spanning tree in the merged districts using Wilson's algorithm, which is a uniformly random algorithm for doing this. And then removing any of these edges will break the tree into 2 disconnected components, which would give you 2 new districts. But we need to find an edge of the spanning tree that breaks the tree into components that have approximately equal total weight or total population. So in this case, we're looking for an edge that would split this tree into 2 subtrees of populations of either 14, 15, or 16 each. And such an edge is called a balance edge. And removing this edge would give us 2 new districts. So in this case, in this tree, there is a balance edge, and the top component of the tree has about population of 14, and the bottom has population of 15. And so in order to do this, the algorithm randomly selects edges from your spanning tree, removes them, and then adds up the total population of each of the sides. And if they're approximately equal within some deviation that you specify, it will remove the edge and you're done. You've created 2 new districts. But if they're not approximately equal, it will just keep choosing edges. And it will do this over and over again, which can be problematic because some trees can't be split into approximately equal pieces. So the red tree is a different spanning tree of these 2 regions, is an example of a tree without balance edges. So Jerry chain could be randomly selecting edges from a tree that has no balance edges. And so to solve this problem, what we do is we basically say, if you don't find a balance edge after this many checks or this many randomly selected edges, then just draw a new tree and then keep checking again. And so I was curious if there was a more efficient way to find a balance edge, or at least just quickly determine that a tree doesn't have any balance edges, so you can draw a new tree and move on. So for example, this is a much smaller example, but it's a tree with total weight 12. And if we check every single edge and remove it, there are no balance edges in this. And so the way that I was thinking about this problem was to change the question into looking for certain edges, but looking instead and look for certain vertices. So in this case, when you remove the vertex V that's highlighted in red, you get a forest, which is basically a bunch of disconnected trees with 5 components. And all of these components have total weight less than half. So there's no edge in this tree that, there's also no edge in this tree that would split it into exactly half. So this is actually true for all trees if they have a vertex that's like this. So let T be a vertex weighted tree with total weight S. An edge E of the tree is a balance edge if the components, when the edge is removed, are such that the total weight of each of the components is in some specified population range. So you maybe specify a deviation D, and then you either you want the weights of your components to be within this range. And so what I found is that if a tree T contains a vertex V such that the tree with the vertex removed, every component has total weight less than the minimum population that you would accept, then T doesn't contain a balance edge. And so we can, to prove this, you basically prove the contrapositive, which is that suppose that your tree has a vertex that you can remove such that every component has less than the minimum that you're willing to accept. And now also suppose that there actually is a balance edge in this tree. And so there's 2 cases for where this supposed balance edge could be. The first case is that the edge E is incident with the vertex that you removed, in which case that this balance edge, the supposed balance edge, would connect the component, one of the components, to the vertex V that you removed, which means that that component has to have weight within your range that you want, total weight within that range. But we already said that every component has total weight less than the minimum that we want to accept, so that can't be possible. And then the second case is that the edge is in one of these components that has total weight less than we want, and so we can't be in there because it would be splitting that component into 2 smaller weight pieces. And you can use this idea to try to find a balance edge, or actually quickly, more efficiently determine whether or not a tree has a balance edge. And the way we do this is to look for one of these vertices that when it's removed, you get components of total weight less than the minimum that you want to accept. So, so let R be the maximum degree or the maximum number of other vertices any vertex is connected to in your tree. And if you have more than one vertex that has maximum degree, select the one with the most weight. So it's weighted the most, or the most people. When we remove that vertex V, you're splitting the tree into the maximum number of components, but you're also minimizing the total weight of the tree. So the average weight of any of the components is going to be minimized. So this is a good candidate for looking for a vertex that would give all components with minimum weight less than them, or total weight minimum less than you're willing to accept. So for example, this tree T, as shown, has total weight of 3.7, and I've set the deviation to be 0.5. So the maximum weight that we're willing to accept would be 2, and the minimum would be 1.7. And so the vertex V that has these properties is highlighted in red. And so the second step is to remove this vertex and look at the components. So you have degree V components, so R components, and you have 3 different cases that can happen. So the first case is that one of your components has total weight that's more than the maximum population that you're willing to accept, which is the case in the tree shown. We have a component that has total weight 2.1, and the maximum that we were willing to accept was 2. So we can't do anything yet. But there are 2 other cases. The first case is that one of your components has total weight within your specified range, and which case you can just take the edge that was incident with this, or that connected this component to the vertex that you removed, and that's a balance edge, since removing that would give a component that has weight within your desired range. And then the third possibility is that none of your components have weight within the range, and they're all below the minimum weight that you're willing to accept, so the minimum population that you're willing to accept, in which case there's no balance edge, so you can just move on and draw a new spanning tree. So in this case, we have a component that has weight that is more than the maximum that we're willing to accept. So we move on to step 3. And step 3 basically says that do the same thing that you did before, but only focus on the component that had maximum weight. So we take the component T1, which had the most weight more than we are willing to accept, and we take the vertex V, BI, or in this case, it's labeled V1, that was adjacent to the original vertex that we removed. And we do the same thing, but with this vertex and this component now. So we remove the vertex V1 and we look at the components of the component T1. So if all of these components have total weight less than the minimum that we're willing to accept, then the tree doesn't have a balance edge. But if one of them does have the weight that we would be willing to accept, then we found a balance edge that was incident with the next vertex that we removed, so V1. So in this example, we get components that have total weight less than we're willing to accept, so we can conclude that this tree doesn't have a balance edge. And here's an example of a tree where we do have a balance edge and the algorithm finds it pretty quickly. So the total weight of this tree is 4.6, and I've set the deviation to be plus or minus 0.2. And so the maximum that we're willing to accept is 2.5, and the minimum is 2.1. So basically we find the vertex that has maximum degree and maximum weight, which is the vertex V highlighted in red. We remove it and we look at the components. We see here that the component that's circled in red has total weight 2.3, which is exactly in the specified range. And it's actually exactly half. And so we can say that the balance edge of this tree was the edge that connected this component K to the rest of to the vertex V that we removed. And so once we remove that, we have 2 subtrees that have approximately equal population, and we're done. And that's basically how you find a vertex quickly, or at balance edge quickly.
All right, so you've seen how we, and Quinn gave you the overview. Katie told you how we get the data. I tell you how they sample the data. Corinne told you about the math behind it. Now let's profit from the data and play with the data. So I'm putting a link in the chat to Districter with New Hampshire. And I'm going to also show you on my screen what we can do with this. So for the state of New Hampshire, let's draw 2 congressional districts out of precincts. So we'll pull up the state of New Hampshire. You can also do California for sure, but you have to draw 53 districts. So it will take you forever. So let's practice with New Hampshire. So this is the state of New Hampshire. We can put some information on here. Like for instance, we can look at the 2020 presidential election. These are how each precinct swung, like a little to the red or a little to the blue. We can change our elections. Here's a previous one. That one looks like it was a little bit more red. The governor, it's a little bit more white. I mean, a little bit like more of a tie. Okay. So here's my challenge for you. So look at, for example, the 2016 presidential election. You'll see that the Democratic vote share in New Hampshire was 50.2%. Republican was just over 50%, just under 50%. And if you prefer a slight Republican advantage, you can go to the the 2016 governor election, which is a slight Republican advantage. And so I'll go to president. Here's what you can do. Here's the fun part. So grab your paintbrush, which is in the blue right now, and make some districts. So in my opinion, the most important thing when drawing districts is how close you are to the ocean. So I'm going to draw a district, and you can see this district I have here doesn't have quite as much population as it needs. I want it to have exactly half the state population. So I need to keep going. Let's do that. Oh, I made a mistake. So I'm going to go get this eraser and erase some until I get back to roughly the population I want. Okay, that's pretty good. Then I'm going to grab my other color. I'm going to lock already drawn districts, make a big paintbrush, and just do the other district is the whole state. Cool. All right, so those are my 2 districts, and that's my new districting plan. So you'll notice it doesn't have any zigzags, unlike the currently enacted one. So good job, me. And the population difference between the 2 districts is only 1.2%. So that's pretty good. And if I wanted to fix it, I could add a little bit to the yellow, but you can do that. Let's go over to evaluation. For the 2016 presidential election, the blue district, the Republicans won the blue district by a tiny bit, and the Democrats won the yellow district by a tiny bit. So my challenge for you is to draw districts such that you get, let's say, a Democratic win in both districts. You have enough to do it. You can push a few of these Democratic votes here into the other one and try to win. And again, if you rather do it with the Republican slight advantage, go over here. Here, the Republicans won this one and the Democrats won this one, and maybe we can try to give some of these Republican votes over to the other district. So if you would, perhaps you could pull that up and try to make some districts and see if you can get two districts to go for one candidate of choice. Yes. Thanks, Quinn, for giving a good link. So while people are doing that, we'll just conclude our talk, and please do that and ask any questions or tell us any great victories you have in accomplishing this task. And thank you very much for your attention.
Oh, yes, let's thank our speakers. As I scroll down to the bottom of the page for New Hampshire, I noticed it specifically mentions you in this group, I think, right? So your districting data at the bottom. So that's very cool.
Yeah, we're the ones that got the data and organized it and cleaned it. So they gave us credit for doing that because it's a big job. Yeah.
So I'm curious. Real quick, but before people, anyone has to head out and hasn't done it already, please sign in a sign-in sheet. There's a link to it in the chat. So I had a quick question for Corinne and Quinn and Katie. I'm curious, how much before this past summer did you know either about either graph theory or about gerrymandering?
I knew very little. Diana gave us a great intro thing to work through. So we all got set up right away.
Yeah, as Diana mentioned, I had the fortune of being in a class with her the semester before, where we looked at the specific problem, and mostly in Pennsylvania. So that was a bit of exposure, but definitely not so much the data collection process was completely new.
Yeah, I did not know the math much behind gerrymandering, but I knew about graph theory and gerrymandering in two separate contexts.
And one more question for me, and then open it up to other people. So I know a bunch of our audience is largely students, and I was just wondering if you had any sort of words of wisdom or thoughts you'd like to share about going through something like this over the summer, some sort of summer RU. Sorry to put you on the spot. No need to. Yeah.
This is weird. I feel like I'm usually the one asking for other people. Yeah, I guess just reaching out to tons of professors and seeing what they're hosting. It's a really awesome experience to get to see different types of things. This summer I'm doing something completely different. So it's awesome to be exposed during that summer time with to different applications of whatever you're studying, or just random other things that you might be interested in.
Yeah, and from the experience we had last summer, one cool thing was that we Diana definitely encouraged us to kind of focus on specific tasks, but also kind of go after whatever else seemed kind of interesting, anything that was kind of tangential to the topic that we were exploring. And that led a team to explore the fascinating realm of prison gerrymandering, which is a whole different whack story, which was really crazy. And yeah, so I guess to make that into a piece of advice, definitely follow your interests, because they lead unexpected places.
Yeah, thank you. All right, so are there other questions? I don't want to hog all the questions here. So this mapping tool, were you guys able to create the kinds of districts that you were wanting to with this? This is maybe not just anyone here. Yeah. There were some nods. I don't know if anyone want to share or discuss.
Yeah, nice. So you can see how people could use it to eke out a tiny advantage, make a tiny advantage into winning everything. And the purpose of this tool is so the community can help. So for instance, I think in California, it's a big deal, or in a lot of places, trying to make a majority minority district, meaning a district where the majority of people in the district are not white. And sometimes the people who draw the maps will say, oh, we don't have any because it's just not possible. Yeah, you wouldn't understand. We have the maps, we can see it's not possible. And by putting this tool out there, you can have there's 28 people in this room. We could all try to do it. I did the data layers being Democrat, Republican, but you can also have it show you races of people based on the census information. And, if 1,000 people tried it, maybe 990 of them would fail, but 10 people might be able to figure out how to draw the kind of district that people were looking for that they just couldn't find before because they didn't have the right kind of tools. So we put the tools, we're trying to build the tools so that no matter what your project is that you want, or what you want to try to figure out if it's possible, you have the tools to try to do it. So I encourage you to try to redistrict California in some way, or whatever state you're from. California is a big job because you have to do 53 districts. And if you mess up somewhere, you might have to redraw the whole thing. But it's interesting. I know we had our task, one of our training tasks was to draw the 18 districts of Pennsylvania and have 2 majority Black districts. And it's easy to get 1, but it's hard to get 2. And you can do it, but it's hard. And then you have to start because you have to get them both in Philadelphia. So you have to start with Philadelphia. If you start like out in the east, in the west, and then you try to get no, can't happen. You got to start here. You can do it, but it's hard. So I encourage you to set some goals for yourself and try it, or tell your friends who might want to do that.
Other questions?
Have you all heard about gerrymandering in other contexts? It's come up before in your life, like in the news. Anybody hear about it in some context they'd like to tell us about?
Someone want to say? So we've had, I don't know where else besides in this colloquium, but we did have another speaker talk on some gerrymandering a few weeks ago using some different ideas or strategies. So the people who would have come to that talk would have seen that. So I'm curious about this sort of this combination and recombination idea. So these algorithms you came up with, I'm curious how efficient they are. You said they're much faster than the sort of you just sort of run it until you a certain number of times, and then you can't find a balanced edge, and then you find a new spanning tree. So
okay, I'll let Corinne take this one, but I want to say, I think I forgot to say this during the talk. Like I should have said it many times. We did not come up with the mathematics and the algorithms. The metric geometry and gerrymandering group, led by Munduchin out of Tufts University, came up with all of it, and we just learned how to use it, and then gathered data to which we could apply it. So it should have been all over the place, like advertisement and credit is due to them. We just used it, so it works great. All right, I'll let Corinne address the content.
Yeah, so the my algorithm runs in linear time, but it actually runs faster for smaller population deviations, and runs but if you have like a relatively large or reasonable population deviation, it runs about the same as just checking randomly, depending on what you set your checking limit at.
But there was a flip algorithm before, just like flipping. It was a much slower thing. Recombination is a very fast thing. If you start with some districting plan and you run recombination like 100 times, maybe it will be completely unrecognizable from where it started. If you start with if you have a reasonable number of districts, even just 100 steps, you're totally far away from where you started. So it's very fast in like mixing. It's like using a industrial mixer instead of like a toothpick. It really mixes things up quickly. All right. Well, thank you so much for having us. It's been great talking with you.
Yeah,
it's good to be in sunny California. It's actually snowing again here, another blizzard. So it's nice to imagine us being on the sunny place with the palm trees and the 75 degrees. So we hope to see you in person sometime. But in the meantime, it's great to meet you this way.
Yes, let's thank them all for coming out and telling us about their project. So thank you guys.